In this video, we're going to use an ANOVA F-test to compare three groups. So in this scenario, we're asking whether a picture has any effect on college students' understanding of ambiguous prose. Students were randomly assigned to three groups. They either saw a picture before reading a difficult passage of text, after reading the passage, or they weren't shown a picture at all. And then all of the groups were tested on their comprehension. This is a theory-based test, so we want to start off by checking the assumptions. The first assumption that's listed here is really just to check and make sure we're doing the right type of test. So an ANOVA F-test is when you have a quantitative response variable observed in two or more groups. So we do have a quantitative response. The comprehension scores are quantitative. And then we have three different groups that we're comparing. These are groups from an experiment. And so an ANOVA F-test is appropriate for this type of data. Second is that the samples are independent and random, so either coming from random sampling or a randomized experiment. And here we do have that. This is data from a randomized experiment. This is important not just for the ANOVA F-test, but in general, anytime we want to think about how we can extend our conclusions. So random sampling would be important if we wanted to generalize to the population. A randomized experiment is important if we want to make cause and effect conclusions. The third assumption is that we want approximately normal population distributions for each group. And this one is a little bit complicated to check because it's sort of subjective, but the general idea is that the larger the sample sizes are, the more skew and outliers we can tolerate. I'll just sort of ask that you mention both the shape and the sample size anytime you check this condition. So looking at the shapes, we can see, they're not perfect. They're not perfectly symmetrical, especially the before group looks like it's skewed a little bit to the left, but also the sample sizes are not terribly small. So we've got sample sizes of 19 in each group. That's, kind of a medium sample size, not terrible. So I would actually probably say that this is okay. We do have medium sample sizes, and let's go ahead and specify that we've got 19 in each group. And just looking at the graphs, I would say no extreme skew. A little bit of skew maybe in one of the groups, but nothing too extreme. I would actually say that the assumption is met here. In general, this condition might be a little bit more forgiving than you would think. And there's actually a word for that. So we would say that this F-test is fairly robust to non-normality. So what the word robust means is that even if it's not perfectly met, even if it's not perfectly normal in each group, that the F-test still tends to give us valid results. So those first three assumptions are things that we've seen before because those three all applied for a two-sample t-test. This fourth one might be new. So the ANOVA F-test requires that the population distributions have the same standard deviation. Again, it doesn't have to be perfect. If we look at the standard deviations here, they're not perfectly equal across the three groups, but a rule of thumb is to check and make sure that the largest standard deviation is less than twice the smallest standard deviation. So here, the largest one is 1.397. And that's not even close to being twice as big as the smallest one, which is 1.256. Another thing to consider is that this assumption is actually a little bit less important when the sample sizes are equal. So when you have balanced groups like we have here, 19 in each group, the standard deviation is not as much of a concern. So I would say this one is definitely met. For stating the hypotheses, we're going to do that in terms of mu because we're comparing the means of this quantitative variable for the three groups. So the null hypothesis will be that all the means are equal to each other. So we could say the mean for the after group is equal to the mean for the before group is equal to the mean for the group that saw no picture at all. And then the alternative, it doesn't require that all of the means be different from each other, just that at least one of these means is different from the others. The test statistic that we're going to use for an ANOVA F-test is not surprisingly called an F-statistic. And sometimes it helps to look at the ANOVA table to sort of see how this is calculated. So let's start off with seeing where these degrees of freedom come from. So the degrees of freedom for groups is the number of groups minus 1. So we had 3 groups before, after, and none. 3 minus 1, we end up with 2 degrees of freedom for the groups. The degrees of freedom for error is the total sample size minus the number of groups. Sometimes you see a capital N for the total sample size, lowercase n for the individual group sample sizes. I won't be super particular about that. So we've got 57 for our overall sample size, minus the number of groups, and we've got 54 degrees of freedom for error. And then the degrees of freedom for the total is just the overall sample size minus 1. So 57 minus 1 gives us 56 degrees of freedom. Notice that 2 plus 54 equals 56. The degrees of freedom always sum up to the degrees of freedom for total like this. So the sums of squares we already talked about, and this is taking into account both SS groups and SS error. So remember, SS groups was looking at the differences between the groups, or in other words, the explained variability, whereas SS error was looking at the variability within the groups, also called the unexplained variability. But the F statistic is standardized, so it doesn't just look at the explained and unexplained as sums. It's actually going to standardize them based on how many groups there were and what the sample size was. So to do that, we're going to calculate what's called the mean square. So the mean square is always just going to be the sum of squares divided by the degrees of freedom. So if we wanted to do the mean square for groups, we would do 35.053, I'm just going to keep 3 decimal places here, divided by 2, and that's giving us the mean square for groups. So basically, how much is explained per degree of freedom. And then same sort of thing to get the mean square for error. We're going to do 94.526, which is the sum of squares for the error, divided by 54, and that's giving us the mean square for the error. So we would end up getting these numbers from the output. 17.5263 is the mean square for groups, 1.7505 is the mean square for error, and then if we put all that together, we get our F statistic. So this is 10.0122. And the way this works in general is that the larger your F statistic is, the stronger your evidence. But we don't really have anything to compare that to. Right now, we don't have any frame of reference for how large an F statistic needs to be before we find the evidence convincing. So for that, we need some kind of a null distribution, either through simulation or from theory. Previously in this class, we've used a simulation to show the values of the R-squared statistic that we would expect to get if the null hypothesis were actually true, and then we can use that to calculate a p-value. We can do the same sort of thing, except instead of recording an R-squared statistic each time, we can record an F statistic each time. So notice that the scale changed here because the F statistic is standardized, so it's putting it on a different scale. But another nice thing about an F statistic is that we can actually use a theoretical distribution as a model. So I'm going to overlay the F distribution here. So this is just using theory to tell us what values of the F statistic we would expect to get if the null hypothesis were actually true. And as long as our assumptions are met, we can use an F distribution to model those values of F that would occur if the null were true, and that gives us a way to skip the whole simulation step. And I'm actually going to introduce a new tool here to explore the F distribution, which is a distribution calculator in JUMP. So before we do anything, let's open JUMP. Then if you haven't already, use the link on ELC to download the JUMP distribution calculator. So it should come up here at the bottom. I'm going to open that, and then just click install. Should be pretty fast. So the way you'll know that it worked is that you should see add-ins up here at the top. So we're going to click add-ins, teaching module, distribution calculator. And this actually allows us to calculate with several different distributions, the normal distribution, the t distribution, which we've already talked about this semester. We're going to use the F distribution. And I'm going to use this screenshot so I can make notes as we go. So just like the t distribution, there's different versions of the F distribution depending on the degrees of freedom. And actually the F distribution depends on 2 different degrees of freedom. One that JUMP calls the numerator degrees of freedom. This is our degrees of freedom for groups, and it's called numerator because it's in the numerator of the F statistic. And then denominator degrees of freedom, this is our degrees of freedom for the error. So when we put that in, this distribution, this is showing us the values of the F statistic that we would expect to get. So the values of F that would occur if the null hypothesis were true. So this is just another way of getting a null distribution, this one coming from theory instead of from a simulation. We're going to put in our F statistic here because we want to know how likely it would be to get that F statistic just by random chance if the null hypothesis were actually true. So even at a glance here, you can see that it's going to be very unlikely. It's actually not even showing on the scale. There is a little bit out there. The line doesn't go completely to 0 yet, but you can just see that 10 is going to be a very unlikely value of the F statistic. And technically, we want to look to see the values of getting F or greater. So we're using the greater than sign here because remember, a larger F statistic means stronger evidence. And so we want to say, what's the chances of getting this F statistic or something even stronger if the null hypothesis were actually true? So we'll actually always use this option for an F test. We won't use any of the other ones. And when we put all this in and it gives us a probability, that's the p-value. It's the probability of getting our F statistic or something more extreme if the null hypothesis were actually true. And we can see that this matches the p-value given to us in the ANOVA table, and it's labeled as the probability greater than F because it's the chances of getting our F statistic or greater. So in practice, it makes more sense just to use the p-value from the ANOVA table, but I do think it's good to know where that value comes from. And either way you calculate it, you end up with the same very small p-value, smaller than any reasonable alpha level. And so I would say that I have very strong evidence here. And whenever we say strong evidence, we always mean evidence against the null and for the alternative. So in this case, it would be very strong evidence to suggest that there is an association, or at least one of the conditions is different from the others. So remember, we can't necessarily say that they're all different, just that at least one of the conditions is different from the others, and we're talking about in terms of reading comprehension. So this isn't necessarily a satisfying conclusion just to say that at least one is different. So in the next video, we're going to learn how to do a follow-up test to decide which of the conditions are different from each other.